Welcome back to the Deep Dive. This is the show where we dig into a whole stack of sources, notes, research, you name it, and pull out the really key insights for you.
Yep, distilling it all down.
And today, we're diving into the secret life of molecules, specifically how they move. Think about it. You don't just stand still like a statue all day.
No way.
You shift, you lean, you find a comfortable spot on the couch. Well, molecules. They're kind of the same. They twist, they bend, they have all these shapes.
And understanding that movement, that flexibility, is honestly the key to understanding pretty much everything else about them.
So for this deep dive, we've got organic chemistry as a second language, first semester topics open, specifically the chapter on conformations.
That's right. And our mission really is to pull out the core ideas, the strategies you need to, really get how molecules choose their shapes and why those shapes are so critical for reactions.
And it really, really matters. This isn't just like textbook trivia.
Not at all.
At its heart, molecules have, let's call them comfortable shapes. Low energy and uncomfortable ones, high energy. These are the conformations. And knowing this gives us predictive power. It lets us figure out how reactive a molecule might be, or even if a reaction can happen at all. It can seem a bit counterintuitive sometimes.
It really can. Think about a lock and a key, right? The key has to fit just so.
Okay.
Well, many chemical reactions are like that. They need the molecule to be in a very specific shape, usually a low-energy one, to work efficiently. If it's stuck in some awkward, high-energy pose...
Reaction just won't go.
Exactly. It might not be able to interact properly with whatever it's supposed to react with. So yeah, predicting these shapes, it's absolutely crucial for understanding chemistry.
Okay, so how do we actually see these preferred shapes? How do we visualize them? Today, we're hitting two really powerful drawing styles. Newman projections.
Which give you this really cool view down a bond.
And chair conformations, which are, well, essential for those six-membered rings you see everywhere. Let's tackle Newman projections first. Get up close with those.
Okay, so when we draw molecules, we often use wedges and dashes, right? To show 3D.
Right. Wedge coming out, dash going back, standard stuff.
But here's a little detail that sometimes gets glossed over. Whether that wedge or dash is drawn slightly to the left or right, that's just convention. It doesn't really matter.
Oh, okay. So it's just about showing front or back, not the precise angle on the page.
Exactly. It's about depth. So keeping that 3D idea in mind, the Newman projection flips our viewpoint completely.
How so?
Instead of looking at the molecule side-on, you're looking directly down a specific carbon-carbon single bond. Imagine putting your eye right up to one carbon, looking straight through it, to the carbon directly behind it.
Okay, I'm picturing that. So the front carbon blocks the back one.
Sort of. In the drawing convention, the front carbon is a dot in the center, and the back carbon is a big circle behind it. The groups on the front carbon attach to the dot, and the groups on the back carbon attach to the edge of the circle.
The source used that two fans analogy, which I thought was quite helpful. Like looking at one fan and there's another one right behind it. You see all the blades.
But sometimes the front blades get in the way of the back ones that can block them or eclipse them.
Right, eclipse.
And that's the crucial insight. Because that single CC bond can rotate freely, this Newman view lets us clearly see how the groups on the front and back carbons line up relative to each other.
So we can see conformations where they're spread out.
We call that staggered, maximally spread out.
Or they're lined up, blocking each other.
And that's eclipsed. And this rotation generates all these different possibilities, these different conformations, each with its own energy level.
Okay, so if we have a regular bond line structure, how do we actually draw its Newman projection? We won't go through the exact drawing steps here. People can look those up, but what's the thinking process?
The key is first deciding which CC bond you're looking down. Then you identify that front carbon and that back carbon.
Got it.
And then, this is critical, you identify all 6 groups attached to those 2 carbons. Don't forget the hydrogens, even if they're implied.
All right, got to count all 6.
Then you mentally position yourself looking down that bond and figure out, okay, which groups are pointing sort of up, which down, which off to the sides on both the front and the back carbon. The Newman drawing just makes that relative alignment super clear.
And once we can see these different rotational possibilities, it becomes obvious they aren't all created equal energy-wise. Molecules prefer certain arrangements. They have comfort zones.
Exactly right. Which brings us to ranking their stability. Let's use butane as the classic example, looking down that central C2-C3 bond. We basically have 2 main families of conformations, staggered and eclipsed.
And you said staggered is generally better, more stable.
Yes, much more stable because the groups, specifically their electron clouds, are as far apart as possible, less bumping into each other.
Okay.
The absolute most stable is the anti-conformation. That's when the two biggest groups in butane, the two methyl groups, are pointed 180 degrees apart, as far away as they can possibly get.
Maximum personal space, like lying flat out in bed.
Good analogy. Yeah, totally comfortable. Then you have the other staggered conformations called gauche.
Gauche. Okay, how's that different from anti?
In gauche, the big groups are still staggered, so they aren't directly overlapping, but they're closer in space, only 60 degrees apart in the Newman projection.
Oh, yeah.
So there's still a little bit of, let's call it steric interaction or crowding between them. They're sort of bumping elbows slightly. It's stable, more like sitting in a chair, comfortable, but not as comfortable as anti.
Gotcha. And then there are the eclipsed ones, the uncomfortable ones.
Definitely uncomfortable. High energy. All eclipse conformations are less stable because groups on the front carbon are directly blocking groups on the back carbon. Lots of electron repulsion, lots of crowding, like standing on your head.
Not fun.
Not fun at all. And the worst of the worst, the highest energy, most unstable conformation.
Let me guess. When the biggest groups are eclipsing each other.
You got it. For butane, that's when the two methyl groups are directly aligned, hiding one behind the other. That's maximum steric strain. That's like standing on your head with no hands, really unstable.
Ouch. Okay, so the stability rule seems pretty straightforward then.
It really is, most stable. Staggered, anti, big groups far apart, least stable. Eclipsed, big groups blocking each other. Understanding this hierarchy is key to predicting how a molecule will behave.
All right, so we've looked down the spine of linear molecules. But what about rings? Those six-membered rings like cyclohexane, they do this whole other kind of dance, right?
Yeah.
Chair conformations.
They absolutely do. And cyclohexane's favorite shape, its most stable conformation, is called the chair. Because, well, it really does look a bit like a lounge chair.
It does. You can almost see the headrest and footrest.
Yeah. Now, when it comes to drawing these chairs, I have to stress this. You must draw them carefully.
Oh, yeah. Why is that?
Again, we're not detailing the exact drawing steps here. Folks can find diagrams easily. But the key takeaway is a sloppy chair drawing makes it impossible to put the attached groups, the substituents, in the right place later on.
And if you can't place the groups right?
You can't possibly figure out the stability correctly. You'll just get it wrong. So practice drawing that chair skeleton accurately. It's non-negotiable.
Okay, message received. Draw nice chairs.
So, assuming we have a good chair skeleton, how do we show where other atoms or groups are attached in 3D space? This is where axial and equatorial come in.
That's it, exactly. Every carbon on the chair ring has two positions available for substituents. One is called axial.
Axial, like an axis. Precisely. Axial bonds point straight up or straight down, parallel to an imaginary axis running through the center of the ring. They alternate. Up, down, around the ring. There are 6 axial positions total.
Okay, 6 straight up or down. And the others? Equatorial.
Yep, the other 6 are equatorial. Think around the equator of the ring. These bonds point outwards, towards the sides.
How do we know exactly which way they point?
They point roughly parallel to the ring bonds that are 2 carbons away. It sounds a bit complex, but once you see it drawn correctly, it makes sense. They're angled slightly up or slightly down, but definitely outwards, not straight up down like axial.
So 6 axial up down and 6 equatorial outward, 12 positions total on the chair.
Correct. And knowing how to draw and identify all 12 is vital because where a group sits, axial or equatorial, massively impacts the molecule stability.
Okay, here comes what I remember being a tricky part. We often see rings drawn flat, like hexagons, with wedges and dashes. How do we translate that into this 3D chair with its axial and equatorial spots?
Right, this translation is key. The first step is understanding the terms up and down relative to the ring itself in that flat hexagon drawing.
Okay.
If a group is on a wedge in the hexagon, we consider it up, pointing up, out of the page towards you, above the average plane of the ring.
Wedge means up.
Got it.
If it's on a dash, it's down, pointing down, away from you, below the average plane of the ring.
Dash means down. Simple enough.
But here's the absolute crucial point, the one that trips up so many students.
Uh-oh. What is it?
There is no direct correlation between being up or down and being axial or equatorial. They are independent concepts.
Wait, say that again? Up doesn't always mean axial, and down doesn't always mean equatorial.
Exactly. On any given carbon atom in the chair, there is one up position and one down position. Sometimes the up position happens to be the axial one, and the down is equatorial. But on the very next carbon, it might be the other way around. The up position might be equatorial, and the down might be axial. Whoa. Okay, that's important. So up-down refers to the overall ring plane, while axial equatorial refers to the specific geometry at that carbon within the chair structure.
You've nailed it. Understanding that distinction is fundamental to getting chair conformations right.
So what's the strategy then for translating the hexagon to the chair?
Okay, systematically. First, number the carbons on your flat hexagon drawing, let's say clockwise.
Okay, numbered hexagon.
Second, draw a nice, neat chair skeleton and number its carbons in the same direction, maybe starting at the top right carbon.
Same numbering direction. Got it.
Third, for each carbon on your chair, mentally, or lightly pencil in, identify which of its two positions is pointing generally up and which is pointing generally down.
Okay, identify the up-down spots on the chair carbons.
Finally, look back at your hexagon. If carbon #1 had a group on a wedge, up, you put that group in the up position you identified on carbon #1 of your chair. If it had a group on a dash, down, you put it in the down position on the chair carbon. Repeat for all substituted carbons.
And that up or down spot on the chair might be axial or equatorial, depending on which carbon it is.
Precisely. You follow the up-down instruction from the hexagon, and you place it in the corresponding axial or equatorial spot on the chair.
And this leads to that weird visual thing, right? Where groups that are trans in the hexagon, one wedge, one dash, can look like they're, I don't know, sort of on the same side in the chair drawing.
Yes. That happens all the time. You might have an up group on one carbon and a down group on an adjacent carbon, clearly trans. But in one specific chair drawing, they might both appear to be pointing, say, generally upwards or downwards visually, making them look cis.
Which seems confusing.
It is confusing if you only look at one static chair. And that perfectly sets up why we need to understand the next concept. Ring flipping.
Ah, yes. Ring flipping. I remember this being another point of major confusion. So what is a ring flip? And maybe just as important, what is it not?
Right. Let's clear this up. A ring flip is not taking the molecule and turning it over in space like a pancake.
Okay, not a pancake flip. That's a common mistake, right?
Huge mistake. Very common. No, a ring flip is an actual conformational change within the molecule.
So what's actually happening?
You're like, the chair is rocking. The carbon that was the footrest flips up and the carbon that was the headrest flips down. The whole ring sort of flexes and shifts into a different chair conformation.
The chair itself changes shape.
It changes its orientation, yes. And here's the consequence. When that flip happens, every single axial position becomes equatorial, and every single equatorial position becomes axial. They all switch roles.
Wow. Okay, so all axials go equatorial, all equatorials go axial. That's a big change.
It is, and this is the other absolutely critical piece about ring flip.
There's more.
Yes. The up or down status of each group does not change. If a group started out up, it was on a wedge in the original hexagon, it stays up after the ring flip. It might switch from being axial up to equatorial up, but it's still up.
Okay, hold on. So the chair flexes, axial becomes equatorial and vice versa, but up stays up and down stays down.
You got it. That up-down designation relative to the ring's average plane is constant through the flip. The axial equatorial description changes.
So that flat hexagon drawing we start with doesn't just represent one chair. It represents this dynamic equilibrium between two flipping chair conformations.
Exactly. The molecule is constantly flipping back and forth between these two chairs millions of times per second at room temperature.
So we need to be able to draw the other chair, the flipped one. How do we do that?
Well, the drawing technique for the flipped skeleton is basically the mirror image of the first one. Again, look up the specific steps. But once you have the flipped skeleton, you renumber it the same way, and you place the groups again, remembering up stays up, down stays down, but now their axial equatorial roles have swapped.
Okay. Draw the flipped chair, put the groups back on respecting up-down, knowing they've switched axial equatorial.
Correct. Mastering this allows you to see both sides of the coin, both conformations the molecule actually exists in.
Which brings us right back to why we care. Stability. Why does comparing the stability of these two flipped chairs matter so much in, like real chemistry.
Because reactivity often depends on it. Like you
Right.
said, maybe a reaction needs a group to be axial, or maybe it needs it to be equatorial. If the molecule spends, say, 99% of its time in one share conformation because it's way more stable, then the position of that functional group in the stable chair is what's going to determine if and how fast the reaction happens. The less stable chair barely exists, so it barely contributes to the reaction.
So stability dictates the molecule's dominant shape, and that shape dictates its reactivity. Makes sense. So what makes one chair more stable than the other? What's the rule?
The fundamental rule is a chair conformation is more stable when its substituent groups, especially the larger ones, are in equatorial positions.
Equatorial's better. Why?
It comes down to steric hindrance, or grouting again. Groups in axial positions tend to bump into the other axial hydrogens on the same side of the ring, specifically those 2 carbons away. We call these 1,4,3 diaxial interactions.
1,4,3 diaxial.
Oh.
Sounds uncomfortable.
It is. It's energetically unfavorable. Equatorial positions, though, point outwards, away from the rest of the ring. Much more space, much less crowding, much lower energy.
So more space in equatorial. And I think you mentioned size matters.
Hugely. The bigger the group, the more it hates being in that crowded axial position. A small group like fluorine might tolerate being axial okay, but a really bulky group.
Like that tert-butyl group you mentioned earlier.
Exactly. The tert-butyl group, a carbon attached to 3 other methyl groups, is massive. It has such a strong preference for the equatorial position that it will essentially lock the ring into whichever conformation allows it to be equatorial.
It forces the ring to flip so it can be equatorial.
Pretty much. The energy cost of putting a T-butyl group axial is so high, the molecule will spend well over 99.9% of its time in the conformation where it's equatorial, even if that forces other smaller groups into less favorable axial spots. It dominates the equilibrium.
Wow. Okay. So if I'm faced with a cyclohexane derivative and need to figure out the most stable conformation, what's the game plan?
Simple strategy. Draw the compound. Draw one chair conformation, placing the groups correctly. Up-down leads to axial equatorial. Then draw the flip chair conformation, switching all axial equatorial positions but keeping up-down the same.
Okay. Got both chairs drawn.
Now compare them. Which chair has the largest group in equatorial positions? That's your more stable chair. If you have multiple groups, prioritize getting the biggest one equatorial. If you can get all groups equatorial, fantastic. If not, minimize the number and size of groups in axial positions.
Compare the 2 chairs, put the big stuff equatorial. That's the winner.
That's the essence of it. That comparison tells you the molecule's preferred shape and likely reactivity.
Okay, almost there. One last thing to clear up another terminology trap. Cis and trans for rings. It sounds like alkene chemistry, but it's different here, right?
For very different contexts, yes. It trips students up constantly. When we talk about a dis-substituted cyclohexane, a ring with 2 groups on it, cis means those 2 groups are on the same side of the ring.
Same side, meaning?
Meaning in that flat hexagon drawing, they would both be on wedges, both up, or both be on dashes, both down.
Okay, cis both up or both down.
Got it.
And trans?
Trans means they're on opposite sides. One group is up, wedge, and the other is down.
Opposite sides, one up, one down.
Crucially, remember, this is ring stereochemistry. The fuvine in cyclohexane means no double bonds. Don't fall into the trap of drawing a double bond when you see cis or trans cyclohexane. The only link to alkene cis-trans is the general meaning. Cis for same side, trans for opposite side. The structural context is totally different.
Got it. Cis-trans for rings refers to up-down relative placement, not anything about double bonds. Phew.
Exactly.
Man, we have covered a lot of ground, from Newman projections giving us that unique bond line view to the whole intricate dance of chair conformations, ring flips, axial, equatorial.
It's a lot, but it's so fundamental.
It really feels like understanding these conformations unlocks how molecules actually behave, how they react. It's like finally seeing the moving parts instead of just a static picture.
Absolutely. And it does make you think, doesn't it? We talk about the most stable conformation, but molecules are constantly moving, constantly flipping, constantly exploring shapes.
Yeah.
So think about biology. Huge, complex molecules like enzymes. They need to bind specific substrates with incredible precision. Could it be that sometimes, for an enzyme to do its job, maybe the substrate or the enzyme has to briefly adopt a slightly less stable conformation, a fleeting shape that's perfectly primed for that reaction?
Huh. So maybe sometimes the uncomfortable position is the one that actually allows the magic to happen.
It's possible, isn't it? That constant dynamic movement, the subtle shifts in energy and shape, maybe that's not just noise, maybe it's essential for function in complex systems. It's definitely something to ponder. The world of molecules is far from static.
That is a fascinating thought to end on. A huge thank you for walking us through all of that, and thank you for joining us on this deep dive into conformations. We hope this helps you tackle those molecular shapes with more confidence.